Welcome back to our series on electricity and magnetism. In this episode, we will be covering three separate concepts. The first is calculating the field from an electrical potential. The second is working out what the potential energy is of a system of charges. And finally, we'll look at how a charged, isolated conductor interacts with the potential and the field surrounding it. First, the field from potential. As we know, we defined potential through force and potential energy. And that definition looked like this. You could calculate the potential by taking the negative integral of the electric field dotted with the path through the field you were going to take to look at the potential difference between two different locations. The integral generally had limits of integration that identified the two positions ds. Well, as we've done with calculus, every integral can really be turned into a derivative, and that's what we want to look at doing now. If we instead rewrite this integral as dv and then remove the integration sign, it's the negative dot product between E and ds. Well, we know a dot product is fundamentally just the product of the two vectors times the cosine of the angle between them. So that means this will be negative E times the cosine of theta, the angle between D and ds, times ds. And that makes this a simple product and no longer a dot product because the cosine theta basically takes care of the s component of the electric field E. Well, if I divide by ds and then I rename E cosine theta as E in the s direction, defined by whatever direction we're going through the field, this is what we get. We get that E in the s direction will be the negative derivative of whatever the potential function is by the variable representing the distance we're going to travel through it. Of course, this needs a direction if it's going to make a vector, and the derivative of a scalar function will never be a vector, so this will be in the s hat direction. And we'll let the geometry of the problem actually determine what direction s hat is. Fortunately for us, most of our electric fields have radial symmetry. And that means as we integrate or differentiate dv ds, they'll just be in the r hat direction. And we'll use the change in potential to determine whether that electric field points inward or outward. So this is really the way it's mostly going to look, is E in the r direction will be negative the derivative of v with respect to r in the r hat direction. Of course, we may also encounter constant electric fields like those produced between parallel plates. And if that's the case, then of course the voltage will just be a linear function of x and its derivative will produce a constant, and that's what we would expect. So if you have the voltage function for any particular area of space, you can always find the electric field in that region just by differentiating based on the variable that the potential is provided in. Okay, our second topic for this episode is going to be on systems of charge and how do we handle energy and potential if we have a system of charge. Well, let's draw a simple system and then see if we can calculate it based on that. My simple system is going to consist of a number line where I've got three positions, 0, R1, and R2. And both those R's are measured from the origin. And I'm going to place three charges at each of these spots. So at spot number 1, we'll have Q1, and it's a positive charge. At this spot, R1, we'll have negative Q2. And at R3, we'll have positive Q3. Now, of course, these charges, based on their configuration, have a certain amount of potential energy. That is, it took an amount of work to get them here. These charges wouldn't naturally form this configuration. There's no such thing as a natural configuration of charges. They all have to be built from scratch. And so what we want to consider is, what energy would it take to build this configuration from scratch? So let's imagine first that this space is empty. It has no charges in it at all. All the charges are at infinity, so they're so far away they have zero potential energy. Now I'm going to bring charge number 1 here and place it at the origin. And of course it takes no energy to do that because there's no charge and no field I'm fighting against. This region was empty. So the first charge comes for free. But the second charge, this Q2, there's going to be an attractive force between them, and I'll actually be fighting against that attractive force as I move it from infinity here. This charge will basically look like an energy well, and this charge will want to fall into that well because it will in essence see a charge that it's very attracted to. So let's see what that amount of potential and potential energy would be. So I'm going to call that U from 2 to 1, and that's the amount of potential energy that 2 is going to gain by being closer to 1. That's going to, of course, be equal to Q2 times the voltage that 1 generates at this location. And of course, the voltage formula is pretty easy. This is going to be Q2 times K Q1 over R. Now, this will be an attractive force, which means I'll get a negative potential from that, and that's of course because Q2 is negative. So if I add the negative in there to take into account the species of the charge, U21, the amount of potential energy between these two, will be negative. Here's an interesting fact too. Had instead of bringing Q1 to 0, I had brought Q2 first and then brought Q1 in later, you'll notice it doesn't matter. This final energy expression works no matter whether Q1 was in place first or Q2. So there's a symmetry to it such that the potential energy between these two charges doesn't matter which one's brought in first. That potential will be constant regardless of order. That's really powerful. Next, let's consider bringing Q3 in. So that's going to require the sum of two terms because there'll be a U from 3 to 2 plus a U from 3 to 1. In other words, there'll be two different potential energies that will be different based on how Q3 responds to Q1 and 2 being present in these locations. Let's look at those terms individually. First, U from 3 to 2. Well, 3 to 2, again, that's going to be attractive, which means it'll be a negative energy. Of course, in this case, Q3 sits outside Q3 times the voltage that 2 would have produced all on its own. Of course, that's going to be a negative voltage. Why do I know that? Because Q2 is itself negative. So this will be Q3 times K negative Q2 divided by the radius. And the radius in this case, of course, is the radius that was the location of Q2. The Q2 to Q3 radius, because it's between those two, is going to be equal to R2 minus R1. So R2 minus R1, and that'll be the distance between them. So there's the Q2 to Q3 part. Of course, there'll also be a second energy in the same association, and that's U31. That's going to be Q3 times V1. And of course, the V1 is the same as it was up here. It's KQ1 over R. But in this case, both of these charges have the same sign. So we're going to gain positive potential. We're going to have to do work in this case. So what's that going to be? That's going to be Q3 times KQ1 over the radius. And the radius between Q3 and Q1 is just R2. And so there it is. There's the energy it took to get Q1 and 2 in place. And here's the total energy it will take to place Q3. If I want the potential energy of the entire configuration, that would be U total. And that's going to be U21 plus U32 plus U31. And you'll notice that of these three, the Q3 to Q1, this will be a negative term. The U21 was a negative term, and it's only the U from 3 and 1 that will actually be a positive term. This will then also equal the amount of work that's done in order to get the charges into this configuration. Now, if I was just interested in the voltage as a result of these three being brought together, I could leave it as V, but I'm really interested in the total energy of the configuration. As you can see, this is scalable to any number of charges. And if there's a geometric configuration of the charges, all that's going to impact is the radius between them. So I'd have to use the geometry to calculate that and then use it in the denominators here. Okay, our third concept is about an isolated charged conductor. Let's imagine that this one is an oblong conductor. That is, it's a conductor that does not have a symmetric surface. And I've chosen this one intentionally because we don't want to get caught up in the idea of symmetry and Gauss's law and all the things we've learned before. Well, I know that if I place any charge on here, that charge will simply occupy the surface. It will move out along the surface until it's distributed. Now, in this case, it is not going to distribute itself evenly. It will actually distribute itself so that its least amount of charge is in the smoothest portions of the surface. And the greatest amount of charge is going to be concentrated in the portions of the surface whose surface curvature is greater. Because what we'll get is field lines that are always perpendicular to the surface. And of course, if the surface is very smooth and has a broad curvature, it will produce a very small field. Notice, this field, the field lines not only diverge, but their density is quite low. Whereas over here, notice these field lines are going to start concentrating as we get closer to the surface, because the surface itself gets closer to itself by having a higher curvature. What that tells me is more charge has to be configured here than here, and that's what produces a larger field here than here. So again, we couldn't use Gauss's law to solve for the electric field here. We'd actually have to integrate the flux at each point on the surface, and we're not going to go there. The thing I want to inform you about is this entire surface, even though the electric field is different at different points on it, the potential is the same everywhere. That is, if I draw equipotential surfaces that get closer and closer to the surface, the final one will wrap right around on top of the surface, so that this surface here, the entire surface, is an equipotential. And of course, we know further that a conductor has no electric field on the inside. So let's recall the very first equation we started with here, that potential is equal to the integral of E dot ds. That is, we have to be moving through an electric field that changes in magnitude in order to get any potential. If the electric field is the same at every location within the field, then we'll get a linear voltage. But if the electric field is zero, it isn't that we'll get zero voltage, we'll get no change in voltage. So whatever the potential here is at the surface, as we move inside by a new ds, we'll be moving through space that has no electric field. So our delta V is going to be equal to the negative integral of E dot ds, and this will be 0. Now, lest you say, hey, delta V being 0 produces 0 voltage, that's not true. The definition of delta V is the final voltage minus the initial voltage, and that's equal to 0. This doesn't say both voltages are 0. This says the change in voltage is 0. That means the voltage remains constant. So V final along any distance from the surface inward will equal V initial. And what that means is the voltage inside of a charged capacitor is a constant. It's not 0. The electric field is 0, but the voltage will be constant. In essence, you can think of it this way. As we integrate from infinity in towards the surface, we'll experience higher and higher voltages until we reach the surface. At the surface, the voltage becomes a constant, and everywhere in the interior, it will remain the same. Okay, so we've looked at 3 separate phenomena here. The idea that we can calculate electric fields from the potential function. We've also looked at how we evaluate energy and voltage for a set of charges, discrete charges. And finally, we've looked at the idea that a charged conductor not only has 0 electric field inside of it, but also a constant potential. And that potential is the same potential as exists on the surface, which is an equipotential surface. This about wraps up our unit on potential and potential energy. From here, we're going to move on to one of the great applications of potential, and that is circuit elements. And we'll begin with the first one, capacitors.